Hi, we're going to talk here about the material in lecture 24. Right, that's the lecture on linear regression. As always, this video is not a substitute for reading the book of notes. In fact, in this case, they have way more information, lots of explanation that I'm not going to give here. Okay, linear regression is about drawing a line through a bunch of dots. Right? Here, let's start with this thing as an example. So what this is a bunch of bivariate data. Maybe you remember that word. Bivariate data. Right? It means data in the form of ordered pairs, x, y. So this is the x-axis, the y-axis. And here, the x-axis has dosages of some medication, and the y-axis shows the corresponding blood pressure readings that patients had when they were given those dosages. Now this data is pretty messy. Right? It's kind of all over the place, but there is a definite trend in it. Right? It isn't just a cloud of dots. It seems to rise, right? As the dosage increases, the blood pressure also increases, and it seems to kind of go right along this track right here. It's not rising very fast, like a curve that would slope up really rapidly. It's not rising really slowly, like this kind of curve here. It seems to be rising more or less along a straight line. It has what's called a linear trend, which is to say it kind of tracks a straight line, even though it's messy and not on the line. What we want to do is we want to be able to draw the line that best represents this data. And when we get that, we're going to call it the trend line. The trend line, it's got a couple of other very common names. It's called the regression line, right? And it's also called the least squares line for a reason you'll see in just a few minutes. Okay. Now, any non-vertical line is going to have an equation that looks like y equal ax plus b. I know that usually you write that y equal mx plus b, but for historical reasons, for regression lines, it's written y equal ax plus b, and a and b are numbers. A is the slope of the line, b is the y-intercept of the line. And in this case, it would be that point right there where it meets the y-axis. The technique, which we're not going to do explicitly, we're going to use the calculator for, the technique finds those numbers, a and b, from the data, from the x and y values. Again, we're going to do that on the calculator, but I do need to give you some idea of where this thing comes from. So let me do another little drawing here. Right? I'll just put in a few data points, like this one here, and this one here, and maybe that one there. Okay, and there'll be a lot more data. But we just want to need a few points so I can point some stuff out, no pun intended. And let's suppose that this is the regression line. So this is the line y equal ax plus b. Okay. This point right here, let's say its x-coordinate is x1, right? And its y-coordinate, of course, would be y1. And then there's also a point on the line here, right, with the same x-coordinate. That point, the y-coordinate, well, this is the line y equal ax plus b, so the y-coordinate would be a times x1 plus b. That's what that y-coordinate would be right there. And we think of using the regression line to predict the y values from the x values. So you plug in an x value, and you get ax, whatever it is, plus b, and out comes the y value. In this case, the prediction is wrong. It's off by a little bit. In fact, it's off by this little distance right here, which we'll call epsilon sub 1. That's not something you have to remember. Epsilon is often used to mean a small quantity in mathematics. Right? In this picture, epsilon sub 1 is equal to y1, this height right here, minus ax1 plus b. Right? Notice that epsilon sub 1 is positive. Right? This number is bigger than this one. This height is greater than this height. If you do the same thing over here, this would be x2, right? And then the height would be y2, only it'll be messy if I write it over there, so let's just write it here. Right? And then there'd be the point on the line with x-coordinate x2, and it would have height ax2 plus b. And so the difference here, right, our epsilon sub 2 would be y2 minus ax2 plus b. Right? Notice that epsilon sub 2 is less than 0, right? Because this point is smaller than the point you subtract off. This height is smaller than the height you subtract off. Right? We're going to assume that these epsilons are pretty small in general, and that actually we're going to assume that they are normally distributed with mean 0, which means that most of them will be small, near 0, with not too many very large, and that there will be just about as many positive ones as negative ones. Okay, what would we do to draw the best possible line? What we would want to do, I think, is to minimize the error. We want to draw the line that causes the least error. So you might start with the total error here. Maybe that would be the absolute value of epsilon 1, this distance here, plus the absolute value of epsilon 2, this distance here, and so on, however many data points you had. Let's say you have n of them, then you'd have epsilon n there. Okay? And you'd want to minimize that. And that would be a very sensible strategy. Right? And that is actually useful. But what the regression line is the line that minimizes a slightly different quantity. It minimizes this quantity right here, epsilon 1 squared plus epsilon 2 squared, and so forth, adding all of them up to epsilon n squared. Again, this is not something you need to know. But you need to remember, it minimizes the sum of the squares here, and that is why it is called the method of least squares, and why the line is called the least squares line. Okay. Let's do an example where we actually calculate the coefficients of the regression line. Okay. We start with a table here that shows the ages and salaries of 10 secretaries at the XYZ Corporation. Now we think of a regression line as, let me go back to this picture here. We think of a regression line as predicting the y value in terms of the x value. So whatever you plug in for the x value, that's what you're going to use to predict. Right? And the y value is whatever is going to be predicted or explained, either one. Right? Okay, let's give the equation of the trend line. Okay, so how would I do that? I would take out my trusty calculator, and I would go to Stat and Edit, and I would put the x values in list L1 and the y values in list L2, and of course I've done that here, so you don't have to watch me do it. And then, to get the coefficients of the regression line, the A and B, you just go to Stat, Calc, and then number 4 there, linreg AX plus B, press Enter, and press it again, and there are A and B. Y equal AX plus B, it reminds you of which coefficient is which. A is the slope, B is the intercept, and then it tells you A is about 109.68, so let me mark that down. A is about 109.68, and B is about 19022.89. Okay? So the equation of the trend line is, and I'm going to write y hat because that's a very traditional way to write this. This is ax plus b, in other words, it is 109.68 times x plus this number here, 19022.89. Okay? That's the equation of the trend line. Okay, the second part here is to use the equation to predict the salary of a 23-year-old secretary. So what I want to do is I want to plug 23 in for x. Right? I'm regarding the equation of the regression line here as a kind of formula where I can plug in values for age and get out a value for the salary. So I'm going to write this as y hat sub 23, right? And that's going to be 109.68 times 23 plus 19022.89. So let's see what that is. It is 109.68 times 23 plus 19022.89. 21,545.53. So this is 21,545.53. Right? And of course those are in dollars. All right. Let's do the same thing to predict the salary of a 35-year-old secretary. Well, we just do the same thing. Y hat sub 35, we'll call it. It's 109.68 times 35 plus 19,022.89. And what does that turn out to be? That's 109.68 times 35 plus 9022.9 and 22,861.69. Okay. Now there's a fundamental difference between these two calculations, which is not immediately seen. Notice that this data here goes from age 20, the x values, they go from age 20 up to age 32. Right? X goes from 20 up to 32. If I plug any number in for x that is between those values, the x values from the data, right, then that is called interpolation. And any time it's sensible to use a linear model to model your data, interpolation should give you a fairly reliable result. When you put in an x value that's outside this range, that's called extrapolation. It makes a difference. Extrapolation is much more dangerous, much more iffy than interpolation. The truth is we can't do without extrapolation, but you want to be very careful. If I were really doing real work, I would never extrapolate as far out past the end of this interval from 20 to 32 as 35. I might be willing to predict the salary of a 33-year-old secretary, but not all the way out to 35. The problem is that it might not, the relationship that this line represents might not hold out that far. In between here and here, given that it's reasonable to use a line at all, which we're going to suppose it is, it should hold pretty well. But outside that range, we have no idea whether it holds. Here's an example of extrapolation gone wrong. First of all, what's in this table? This table shows the global temperature anomaly. I'll tell you what that is in a second, though it's in parentheses there, in degrees Celsius for the years 1950 to 1969. Well, the way you get the global temperature anomaly is you find the average global temperature for every year for the whole 20th century, and then you use that as a sort of baseline. And then in a year when the average global temperature is different from that baseline value, the difference is the global temperature anomaly. Right? And you can see here in 1950, the difference between the average for 1950 and the average for the whole 20th century was pretty small, right? Minus 0.17 degrees. It was a little below. 1950 was a little below the century average. And it stayed mostly below or right near the century average all the way through 1969. Okay, using this data, and this is 20 years of data, using this data, we find the coefficients for the trend line and use that trend line to predict the anomaly for 2016. Now remember, this is going to be a kind of extreme extrapolation. This data only goes up to 1969, and this is asking us to predict something about 47 years later, which is way, way too far. So you could expect it to go wrong, and it does. So you plug all this data into the calculator, and you find that A is about 0.004, B is about minus 7.853. So you get this regression equation right here. And if you plug in 2016 for X, which is the way you use these lines, you get a value of 0.211. That is less than a fourth of what the true value actually was, right? Here is the picture of the data with the squiggles going through it. And here's the trend line that tracks the data between 1950 and 1969. 1969 be about right there. Right? It does track the data pretty well between those years, right? The data is certainly not on the line, but it's not far from it. You can see that it's just increasing slightly. But somewhere around 1975 or so, the trend began to take off. It actually became exponential. Right? The global temperature anomaly rose much more quickly than it rose on this trend line. And so if you extrapolate all the way out to 2016, you get a value that is much, much, much too low. Right? The moral of the story, beware of extrapolation. Right? Be very wary about using extrapolation.